So now we'll go beyond least squares. However, let me mention that the technique that we're going to cover this week is least squares, which has already been covered. And what we'll follow is essentially a broad overview of a variety of different areas dealing with different types of prediction models and their relationships, which are increasingly becoming apparent in the research community. Let's first see what happens if we have categorical data. That is, that the target variables that we're trying to predict, the y's, are not numbers but yeses or nos, which is essentially the learning problem that we had earlier. But the challenge here is that the x's are still numbers. So it might not be such a great idea to use something like a naive Bayes classifier, because one would have to discretize those numbers into categorical variables, which might not be appropriate. So one tends to try to use regression techniques, but using a linear regression, when all one is trying to do is separate out the no's, which is the reds, from the blues, which may be yeses, is quite brittle, because the points right near the line might get classified either way, and the distinctions one has to make are very small and are subject to a lot of error. The other problem, of course, is that there may be no such line separating the data, and we'll come to that in a minute. But just to make regression work for categorical data, what the most common technique being used today is logistic regression, which essentially replaces f by a function of the form 1 over 1 plus e to the minus f transpose x instead of f transpose x. Let's see how this function behaves. First of all, suppose f transpose x is 0. Then clearly the second term, e to the minus f transpose x, in the denominator becomes 1, and we have f of x is 1/2. Now if f transpose x is very large, that is almost infinity, then e to the minus f transpose x is almost 0, and f of x is close to 1. On the other hand, if f transpose x is very, very small, that is close to minus infinity, then the denominator in this expression becomes close to infinity, and we get f of x is almost 0. In each of the cases, whether it's tending towards 1 or tending towards 0, this particular f of x increases or decreases much more rapidly than plain old f transpose x. In fact, the graph of f transpose x looks a lot like the S function that we used in our very first week, that is the locality-sensitive hashing lecture. It's a different form, but the purpose is pretty much the same, to have a function which is close to half, but decreases or increases very rapidly away from 1/2 as f transpose x increases or decreases. So the speed at which the second term deviates from 1 is what makes the logistic regression particularly attractive, to separate out the yeses from the nos. Of course, trying to fit such a function is not as easy as linear least squares, but we'll show how that can be done very soon. The other problem with linear regression is that the data might not be separable using a line. So one might, for example, you might have a parabolic relationship, as we described earlier. To support more complex functions, and where one doesn't even know what kind of function to have, the technique called support vector machines have become very popular. And there, the kind of function f is parameterized by kernel parameters, and these parameters are also learned along with the function itself. So not only does we learn the function, but we also learn the type of function from the data. And so if it's a parabola, we'll learn a parabola. If it's something more complicated, like a circle with rather like a donut, the support vector machine will learn such functions as well. The point I'm trying to make is that starting from linear least squares, one increases the complexity of the functions one is trying to learn, and we arrive at other types of regressions and support vector machines. Way back in the early days of the AI, one found many efforts to mimic the brain, which essentially resulted in the field of neural networks, where one tried to create structures that sort of looked like how neurons in the brain affect each other based on their connections to other neurons. The first neural networks created in the 50s by McCullough, Pitts, Rosenblatt, and others essentially looked like linear combinations of inputs. So they were pretty much like least squares in the sense that you could have a neural network which would say that there's a neurons, and the input to this neuron is the rainfall, and this one's the temperature, this one's the harvest rainfall, and then we have another one which has just one, and the output would be the wine quality, and the weights, that is the connections between these neurons, would be learned by a process of iterative refinement, which could be essentially looked upon as a way of solving the least squares problem. To deal with exactly the same problems of classification, we found logistic functions being included in neural networks. So essentially this field was evolving parallelly to statistical prediction techniques. And interest in neural networks sort of waned over the years. Along the way, of course, we figured out different types of neural networks which were multi-layer, and essentially by a combination of logistic functions, linear functions, and other types of functions, one could learn more complex nonlinear functions of the input variables. Hidden layers were introduced, which were essentially creating more complicated forms of f, and parameterized by the weights, which would then get learned through a process of optimization, as we'll see shortly. Finally, in recent years, in spite of the fact that interest in neural networks has waned over the years, these have become interesting once again with the notion of feedback. Notice that these networks that were shown here, all the links go forward from the input nodes to the output node. So they're feed forward even though they're multi-layer. But when we start having feedback, that is that an input, a node in the middle, output is fed back into the previous nodes, this starts behaving like a Bayesian belief network. In particular, feedback neural networks display the same kind of explaining away effect which we found in Bayesian networks, that once you figure out that something, a particular cause is more likely, other causes which might also contribute to this input node become less likely. So that makes this much more interesting than the older neural networks and has sparked much recent interest in this field. The field of deep belief networks, multi-layer feedback neural networks, temporal neural networks, all this are all coming together, and deep relationships between them are being explored. We'll come to these points soon. But for the moment, let's try to understand, if one has such a complex f, how would one learn the parameters of f?